what if I told you that you could build your own YouTube-like platform from scratch? Sounds crazy, right? But in this video, I will show you exactly how I designed and built a scalable video streaming platform using microservices. This video isn't just about the code, it's about the thought process behind designing a scalable and efficient system. So in this video, I'm going to tell you exactly how I designed the system architecture, why I chose microservices over Monolith, how authentication, video upload, comment, search and streaming works together, and how I use Docker to bring them all in one place. At first, to me, a monolithic app just sounded fine. Everything's in one place. The functionality was just basic. And this is exactly how I started. I started with a basic streaming platform where users could upload and watch videos. But as I added features, things were a little mess. When I introduced a separate video upload function, errors popped up everywhere and everything was so jumbled up I had to stop and stare at the errors and try to figure out which function of video stream or video upload was causing this error. So I had to stop and reiterate my idea, and then I decided to go with microservices. And why I chose microservice is because I needed my system to be scalable, independent, where every service will run separately and fault tolerant. Basically, it means if one of my services fails, the others were still functioning. Instead of building a single large app, which basically Monolith does, I broke down my application into 5 powerful microservices: user authentication, video upload service, streaming service, search service, and comment service. So now, as multiple services were running, I needed a way for them to communicate efficiently without hard coding their location. That's where I used Service Registry. And this Service Registry, what it does is that each microservice will register itself here and other services will query the Service Registry to find their dependencies. And this will help us avoid hard-coded IPs and allow dynamic scaling. So let's take for an example. When the front end calls the video upload service, it doesn't need to know the exact IP of that service. It just asks the service registry. So think of it like this. Instead of memorizing your friend's address, you just check Google Maps. That's exactly what the service registry does. And this makes system flexible. And now at this point, I had a basic app up and running that allowed users to upload and stream videos. And let me tell you how this basic app worked. User will upload their video via frontend React using an upload form. Then this selected video was sent to the backend and upload service will save them in the app/videos directory. And for streaming, when user clicks on a video in the front end will send a request to the video service for the file, and then this video service will read the file and stream it back to the front end. And now everything was functional. But there was this one major issue. I didn't want random users uploading inappropriate or unauthorized content on my platform. Security is everything, right? So that's when I decided to upgrade the app by implementing JWT Authentication to ensure that only authenticated users could upload videos. A video uploading platform needs users to log in before uploading or even commenting, right? So for this, I created auth service. So when a user logs in via the front end, this auth service will validate the user credential by checking the user exists in database or not. Then if it exists, it is going to verify their password using the bcrypt library. And once that is verified, this will generate access token, which will be used for authenticating API request, and it will also generate refresh token, which will be used to generate a new access token when the current one expires. And now I wanted persistent authentication. So instead of storing the JWT in local storage, which is insecure and does not persist authentication properly, I decided to store the access token in secure HTTP only cookie. This will ensure that the token is automatically sent with every request, allowing seamless authentication. And when the access token expires, the front end does not ask the user to log in again. Instead, the refresh token, which was stored securely in MongoDB, will be used to generate a new access token, ensuring continuous authentication. And once users log out, we also have to remove the refresh token from the MongoDB to prevent its further use. And we will also clear the cookies for fully logging out the user and ensuring no session remains. And now if I deep dive into the uploading mechanism, here is another problem. How do I track which user uploaded which video? Second, how do I ensure that only authenticated users can upload? Third, what happens if someone uploads the same video twice with the same name? Let me give you a spoiler over here. It replaced the old one. How I solved it is I utilized Multer library to handle the file uploads. Second, I used the custom storage logic inside this Multer function, which will generate unique file names. And then, of course, database to store essential video details. And as I told you, to prevent overwrites, I use Multer for file uploads and added a custom storage function inside it. This function will help us generate unique file names based on a timestamp and random string. And now every video upload will get a unique file name and no more overrides will be there in our application. And now the file names that are unique, I needed a way for them to link to the users, right? That is where we use MongoDB to store video details along with the user ID and username. And now after all these changes, how did the upload API worked? Let me tell you. Now the front end will send a video file and authentication token. Then this authenticates user middleware is going to check if the user is logged in. And if they are logged in, then this video will be taken and Multer will save the video with a unique file name generated by the custom storage logic function. And then we will store this video metadata into MongoDB database. And finally, the backend will respond us with the success message and the video details. And this ensured that every video was securely stored and it was properly tracked and linked to that user. And now let me tell you how the streaming worked. User clicked on the video on the front end. Then this front end requests the video service for the file. Then this video service fetches all the video metadata stored in the MongoDB. And once it gets the list of the videos, it will return that list of videos for the front end to display. And this is exactly how user sees a list of available videos on the platform. And to stream a particular video, the front end will send the request to the video service. Then this video service will search into the MongoDB database for that particular video by the title name or a file name. Then this file, once received from MongoDB by the video service, would be streamed to the front end. And now user could directly access a video URL to stream it. And this made it easy to deliver the video content to users seamlessly. And then I did not want users to scroll endlessly to find a video. How about we built a search service that filters videos instantly? That's exactly why I built Video Search Service. It will help users to search for videos, fetch videos by the username, and even retrieve the video's detail. All this in real time. For this, I needed my search service to connect to the video metadata MongoDB database, which will ensure all the video metadata is accessible for searching. So now user could search for videos based on the query, and query would be any word or a sentence that they are typing. How this worked is the front end would send a search request to the search service, and it will take query as a parameter. And then the search service, which is basically the backend, will scan the MongoDB for the videos for matching titles or the description or basically keyword that the user has typed in. Then this service will respond with the list of matching videos which has that particular keyword. And then this exactly video details page. On the right side, you see that we are getting videos by user names, right? So for this, I also added a functionality which showed videos of the user beside the currently playing video. So for this, I had to create another endpoint which is user videos. This API retrieves all the videos uploaded by a specific user. So the front end now would send a request, and this request will have username as a query, and then its value would be that particular username. Then this service will fetch all the videos uploaded by that user, let's say for example test user. Then the response will include the video titles, upload dates and other details, and it will show on the video detail page. And then finally, comment service. Videos are more engaging when user can share their thoughts, right? So why not create comment service to allow users to comment on videos and view comments for each video in real time. So to add a comment, so the user have to submit a comment via the front end. Then this comment service will receive the request and validate it. Then this comment would be saved in MongoDB with these video name, username, and comment and timestamp details. And now each video has a history of users' interactions. Okay? And to get all these comments uploaded by the users, we will use GET request to get the comments for that particular video. The front end has to request the comment service and it will give the video name. This comment service will fetch all the comments from the MongoDB database, and then the response will return the list of comments for that particular video. And now user can see all the discussion that is happening around that video. And now finally everything was sorted. I needed a way to run everything together. So instead of setting up each service manually, which was legit painful, I used Docker and Docker Compose. What I did is, in the root of the every service, I had to create a Docker file so that each service run its own container. And then these containers will talk through a shared network. Then MongoDB and video storage would help us persist across restarts. And now, instead of manually starting every service, I just had to enter this one command in my terminal and my application would run as one system. And the command is, you guessed right, Docker Compose --build. And with this just one command, my entire platform started running. And now services were isolated, but yet they started communicating efficiently. And with this, our whole application was ready. And that wraps up our video on microservices based video streaming platform. We covered everything from setting up video uploads with authentication to storing metadata in MongoDB. And now I hope that this video was helpful. And if it did, then please let me know in the comment section below. If you have any questions or even suggestions, please feel free to drop them into the comments. I would be really happy to answer your doubts and view your suggestion. And if you want this project's code, do not worry, I have left the link for its GitHub repository into the description. Alright, then I will see you in the next video. Till then, bye bye and take care.